Hello and welcome everybody to the UPRT Experts Corner. We've got a very interesting topic today. We're going to be talking about the value of transonic and supersonic training in upset prevention and recovery training. And I've got two perfect guests to talk with us about that today. First, I'm going to introduce you to, first of all, let me introduce myself. I'm Randy Brooks. I'm the Vice President of Training and Business Development at Aviation Performance Solutions. We deal with a whole host of different platforms in upset prevention and recovery training, and that's why we wanted to focus in on this component of training. Joining me to discuss that initially is going to be my co-vice president, Clark Otter McNeese. Welcome, Clark. How are you doing today?
Doing great. It's great to be with you, Random, here.
Yeah.
Full Phoenix at our new headquarters here.
Let me tell the folks a little bit about you. So Clark and I met in, I believe it was 2010, as part of the FAA's Stowe Stick Pusher Industry Working Group that rewrote an advisory circular 120-109, now 120-109 Alpha, on stall training. But Clark is a former naval aviator, flew F/A-18s in Desert Storm, grew up flying gliders and little airplanes before he went into the Navy, did his Navy tours and left to work for a major air carrier in the US for about 10 years. And about half of that time, about 5 of those years as a captain. And then he decided to devote use all of that time and talent to join Aviation Performance Solutions, where he has now been working for, how long have you been at APS, Otter?
16 plus years, full time.
16 years. And because of that expertise, he has been invited to help ICAO to introduce UPRT at a variety of locations around the world. He's helped to train the instructors that work with us at Delta Airlines and United Airlines. And great to have you here, Otter. And I'll before I leave, I'll introduce or just add in our guest speaker for today. Steve, just wanted to say hi before I leave, and I'll let Otter do the introductions.
Okay, good morning.
Thanks, Random. Steve, it's great to talk to you. You're joining us from where in the country?
Portland, Oregon.
Beautiful Portland, Oregon. All right, awesome. Well, everybody, I'm just super glad to be working with Steve again. He's been not only a friend, but a longtime colleague in helping deliver UPRT, as well as educate aviators and improve safety. He's got a long list of experience there. You will see from his background. Currently, he's the president of Aircraft Certification Experts, a company he started. They're ACE. In fact, you can see his logo there in the top right. There, he's been through Air Force Test Pilot School. In fact, he was the chief test pilot there for the Air Force. A lot of testing throughout the industry, including Embraer or Bombardier. He's a contributor to ICAO, our Airplane Upset Recovery Training Aid, Revision 3. Flew for Delta for over 15 years, a captain on the 727, 737. So, Steve, it's great to have you. I know this is kind of a passionate topic for you, isn't it?
Yes, it is. It's a good topic to discuss, because one of my areas of concern is high altitude operation, which of course includes the transonic regime.
Yeah, I agree. We see that there seems to be a good number of gaps of knowledge and even skill sets related to high altitude. And that's really what we're addressing here, is high altitude, especially for jet pilots. They're going to be operating above 25,000 feet in the transonic speed range in all. We are going to talk a little bit about supersonic flights and training in that regime toward the end of the presentation. But let's first delve into Transonic. Our goal in this presentation is enhance your practical knowledge of transonic speed characteristics at and beyond VMO and NMO, as well as provide some recommendations for handling overspeed conditions. And then we'll present the value of supersonic training in UPRT toward the end of the presentation. So first up to bat, just to mention some recent high visibility overspeed events, such the Airbus A380, there's a Challenger 604 wake turbulence encounter, also 737 MAX accidents. Certainly everybody's familiar with those. Atlas Air might not be the 767 freighter going into Houston, and then an A340, Airbus A340 over the Alps. Not well known, but very recent overspeed that led to an upset. We're actually going to touch on that particular one here briefly in just a little bit. But what I think we'd like to do, Steve, I think you've got a question. We'll just do a quick little poll for everybody that has joined us. You can go into your chat and answer this question. Have you ever experienced high-speed buffet in level flight or 1G flight? Have you ever experienced high-speed buffet in level 1G flight in your aircraft? So go into your chat, give us an answer. Random's going to be kind of looking over those there and seeing how many we've got there that answer affirmative to it. While you're doing that, let me just give you a quick overview of a South African Airways A340 that had an overspeed event. And basically, here's the sequence of events. They were in normal flight into the long 11-hour flight in the middle of the night over the Alps, normal cruise speed. They had a massive shift in winds, and I'll show that here in a second, which led to an overspeed, a very significant overspeed. They ended up disconnecting the autoflight system and going into a climb, led to speed decay. They went into a stall. There, they ended up being very challenged from an overspeed now to a stall. There was confusion and things. And then they managed to use their UPRT training. Interestingly enough, the report of the investigation, they directly attributed their UPRT to success of the recovery, returning the airplane back to normal flight and then landing safely. In fact, here's kind of what happened. They were flying along normally. They had a 64 knot tailwind, and then over a 14-second period, they actually lost 41 knots. 41 knot decrease, and that is what led to their overspeed. So we'll come back to that briefly here in a minute. Random, can you tell us what are you seeing on the chat on how many have experienced?
Our good friend Skip Johnson is listening today, and he's said that he has experienced it, but not in an airliner. So you'll need to kind of go into that for the folks, since we don't have a lot of folks that may have experienced it themselves, but I know that's one of the subjects that you guys are planning on addressing.
Okay, great. Steve, shall we jump right into here? I'm going to kind of let you carry the ball here a little bit. I'll certainly interject along the way. Do you want to start us off with some thoughts on this?
Yes, well, we're going to talk about transonic flight first, and then go to supersonic flight. We're going to talk about transonic flight because that's where we spend most of our time at cruise altitude and cruise speed. Let's talk about what transonic means. Transonic comes from a term coined for a supersonic airplane. And it's the transition from where the airflow is completely subsonic to completely supersonic. So before the Mach meter will read Mach 1, the speed over the wing at some point is at Mach 1 sonic speed. And then as the airplane continues to accelerate, at Mach 1, there's still this bubble, the bow wave out in the front that's still subsonic, and then it finally pushes through that at about Mach 1.1 or 1.2. So from about 0.7 to 0.8 to 1.1, 1.2 Mach is the transonic regime. Now for our airplanes, of course, we operate in the transonic regime as well, because at our cruise speeds, the flow over the wing at some point becomes supersonic, and that's somewhere again around 0.7 or so, depending on the thickness of the wing and those things. We have a limitation, and I'm sure everybody knows their VMO, MMO, and on the PFD is shown in this slide. There's a barber pole there, and you mentioned the high-speed excursion into the barber pole, and I read in an Airbus Safety Mind that came out in summer of 2019 after the South African A340 incident that addressed overspeed excursions. And we want to try to get the point across that if you go into the barber pole, you're not going to die. There's no cliff-like, that means sudden change in the aircraft handling qualities or the strength. You're not going to break up if you go into the barber pole. So if you get one of those quick excursions, as you might find, say in mountain wave over the Alps, over the Rockies, the reaction to that doesn't require any drastic action. You don't need to pull back on the stick, turn off the autopilot, and pull the airplane up 7,000 feet per minute climb. And the Airbus article for the Airbus airplanes says give the automation a chance. And they mentioned in that article that they had some data that said the occurrence of overspeed incursions is 1 in 1,400 airline flights. And not sure where that data comes from, but that's quite often. So let's go to the next slide. In the general aviation airplanes, we have a airspeed indicator which has green, yellow, and red, and we're all familiar with that concept with many different parameters. But on our PFDs, we have basically a green and then red. Go to the next slide. And you all know those limitations as VMO, MMO. What our PFDs do not show is the margin that you have to dive speed, VD, or dive Mach, MD. And their certification requirements for transport aircraft, which for the FAA is Part 25. There is a significant margin beyond MO and VMO until you will be endangered by regulation, and we have to demonstrate this in flight tests. Is once you go beyond that green line there, there's no cliff-like change in handling qualities or your structural capability. You have to be able to go all the way out to MD, VD, and recover safely without any unusual or pilot skill. So,
hey, Steve, this is really good stuff. It's true as well that you can feel free if you're flying an aircraft with speed breaker spoilers, that you should be able to pull the spoilers even beyond your MMO or VMO all the way out to, isn't that correct?
Yes, in fact, we have to demonstrate that you can safely deploy the speed brakes at VDMD. Now, some airplanes will have a schedule where they don't, the panels don't deflect as much based on some Mach schedule, but you should be able to deploy them. In some airplanes, they even deploy automatically if you get an overspeed. So yeah, you can do that.
You know, I just want to emphasize here, because you said it, and it's so key, is that we need to understand that just because you have an excursion beyond MMO or VMO, you're not going to have a handling or controllability problem all the way out to MDVD. In fact, I was reading through the FARs just a little bit ago to kind of refresh myself on this. Even as you approach MD or VD, there cannot be a significant change in controllability or stability as well. Isn't that true?
That's true. There's no, like I said, there's no cliff-like change in handling qualities or stability. So I don't know what simulator instructors are teaching out there, but we want to make sure you understand that you have adequate margin beyond MMO and VMO.
Awesome. So this next one, this slide here is actually showing an Airbus. In fact, this was actually out of an A340 there, and you can see this aircraft is already in overspeed. They're beyond the barber pole. In fact, the acceleration caret is showing that they're still accelerating. And this is kind of what that A340 crew experienced. They're in that mountain wave over the Alps.
Yes, and if you go, before we go to this slide, just hang on there for a second. If you get in an overspeed excursion, you should know your overspeed procedure. In the Airbus safety mine, number 20 or 21 that came out. And by the way, I recommend looking at the Airbus Safety Mine magazine. It's online. You can Google Airbus Safety Mine and you can read it for free. They have a lot of good articles, most of them written by their flight test department. And they have some very good information. And what they recommend is to let the automation give the automation a chance if you hear the overspeed warning, as opposed to clicking off the auto throttle and the autopilot right away. Is give the automation a chance, and it will probably work. And you got the speed brake handle as well, and you don't need to do anything drastic at that time, as I said. Now the in flight test, we spend a lot of time. I'll spend on an envelope expansion flight when we're doing flutter. We'll spend hours in the barber pole, and you're flying around with, basically the airplanes is okay. You're gradually increasing your speed out towards MD or VMD, and we'll spend hours in there, and it's not a big problem. That's not to say you shouldn't be concerned. By all means, if you get this overspeed warning, be concerned, take immediate action, but don't put yourself in an upset.
Yeah, we don't want to over control the airplane, and certainly we want to, as you said, follow the OEM's guidance right on the overspeed. Most OEMs are going to give recommendations on what you should do if you encounter an overspeed. And a lot of them are, frankly, leave the autopilot on, right? And try to let the autopilot handle it.
Right.
Okay.
Let's move on to the next topic I wanted to talk about, which is the so-called high-speed buffet and the buffet boundary. What you're seeing on this slide is out of a KC-135 flight manual, and it's out of the Section 6, the flight characteristics chapter. It's not a performance chart. It's a chart that illustrates the buffet boundary. And what it shows is there's a kind of a continuous buffet boundary that goes from low speed to high speed, and it kind of blends in. It's not that you have low speed buffet on one end of the envelope and high speed on the other end. It's actually continuous.
Steve,
There's some angle of attack and Mach number combination where you will get buffet. And what is buffet? Buffet is buffet, and it's caused by disturbed air flowing over the tail of the airplane, over the vertical tail and the horizontal stabilizer, and that rough air will cause it to shake a little bit. And a structural response, you'll feel it in the flight deck. If you've ever water skied, you know if you go outside the wake, you're over smooth water, especially if there's no wind, and it's a very smooth ride. And then if you go back into the wake, you're in that bubbly water, and it's shaky. That's kind of what buffet is. And at the onset is where you feel that first tickle. We used to call it the edge of the burble in Air Force flight training in the T-38, and you would fly that you would get your best turn performance if you were right on the edge of the burble, not into heavier buffet, not completely free of buffet, but your best turn performance would be on the edge of the burble. So that's what we're talking about, and I want to discuss that a little bit more using this base type of chart. And let's go to the next slide.
Hey, Steve, let me just point out before we do, just make sure everybody sees, we're talking about angle of attack on the left, on the vertical axis, and Mach number on the right. And just point out that you've got a total of 6 curves there. The top right 3 curves you can see are 3 different weights of the aircraft, but they're all at 40,000 feet. And then the bottom left curves are at, again, different weights, but they're at 20,000 feet. So you can see right there that this definitely altitude is going to affect where your buffet boundary is.
Yes, and as you can see from that chart, as you go to higher altitude, you move up and to the right. And on that chart up there at area D, you can see it's kind of an illustration of coffin corner up there, where your speed range from low speed buffet to high speed buffet becomes smaller and smaller. And we'll go into a discussion now on low speed and high speed buffet. The upset recovery training aid says there's 2 kinds of buffet: low speed and high speed. There's 3 ways this is manifested in the airplane. Low speed buffet is mainly subsonic airflow, and it's due to angle of attack effects. You increase the angle of attack, and the air at some point will start to separate. On the other end of the spectrum, Mach buffet is where you have shock waves present and compressibility effects. And when we talk about the transonic range, we are in the range of compressibility effects. One of the main ones you should know is that as Mach increases, your lift capability of the wings decreases. So the CL max that you can achieve goes down as your Mach increases. So from about up to about Mach 0.3 or 4, the CL max is pretty much the same. As you go from there, from 0.4 out to say MMO, it will decrease quite a bit, maybe become half as much. So those are compressibility effects. So at the far end, right end, is Mach buffet. That's where shock waves will cause separation behind the shock wave, and that will go, that rough air will go back to the tail, and shake the airplane. In the middle is what I call G buffet. That's my term. We used to use that in Delta Airlines as well. G buffet is when you're in the transonic range and you go into a turn. As I said, buffet is buffet, whether it's from speed brakes, you put the speed brakes out and it causes the air to be rough, and that causes some buffet. If you go into a turn at high altitude, there's some amount of G, some amount of angle of attack, where you will get the buffet onset. And that's a combination of angle of attack effects and shockwave effects. As you increase the angle of attack, the airflow has to go faster over the wing, and it increases the shockwave intensity. How do you get there? Well, the low speed buffet is going slow. So if you're in level flight and you go to idle thrust and slow down a level flight, you will get the low speed buffet. On the other end of the scale is going fast. If your wings level and you go to max power, and depending on your weight, you may not be able to get to high speed buffet level flight. Usually you would have to go into a dive in a transport airplane to get to any Mach buffet, if there is any Mach buffet. And then in the middle is the turn, and you can certainly get the G buffet in a turn. So you have this boundary of buffet. Just mention these four cases. On the lower left there, the onset of buffet at low altitude is probably after your stick shaker, if you have a stick shaker, or after your angle attack protection kicks in. Especially as you get into configurations with deeper flaps, such as your approach or landing configurations. High altitude stall, you're going to be clean, of course, no flaps, no slats, and you will get buffet, and it will be for the stick shaker. The high speed buffet, and this is the point I want to make, an important point. High speed buffet will always be greater than MMO in a Part 25 certified transport airplane, because it's the law. I can't sell you an airplane that we make that has high speed buffet within the cruise envelope. And MMO is a perfectly normal cruise speed. You can cruise at MMO if you want to. But we're not allowed to have Mach buffet. The way it's worded is in straight flight. That means wings level and either constant altitude, or you could be in a dive. You can't have Mach buffet in the normal envelope. And most airplanes now won't even have that until approaching MD or beyond MD. And one of those safety minds that Airbus has, they point out that their airplanes do not have Mach buffet all the way out to MD. So,
hey, Steve. All right. So I just want to reiterate here that this is what you're saying, and that is that you are not to have buffet really at all the way to MMO in straight level 1G flight. However, you could get G buffet if you go into a turn and you're still below MMO.
Correct. Yeah.
Okay.
Buffet from stall warning buffet is allowable, of course. Buffet from speed brakes is allowable. Buffet from high speed Mach buffet is not allowed up to MMO.
All right, great.
If we experience that, we have to go back to the drawing board and change something in the design.
Okay.
The test pilot might experience it, but the line pilot should not.
Great.
And like I said, even if you get into an airspeed excursion into the barber pole, you're probably not going to see that. Now,
Awesome.
if you pull up, you probably will, because you're putting G and you're going to get G buff.
Yeah.
Back
All
to
right,
you.
great. And I think we just wanted to emphasize here that this applies to not only Part 25, but the EASA certification as well as Transport Canada and pretty much worldwide in certification of aircraft, correct?
Correct. The rules are basically the same concerning the vibration and buffeting section. You can look it up, Google it, Part 25.251 and 253, and read about those things. It's interesting.
Okay.
Now,
all right. You want to talk about this?
This is going to explain this a little bit more. This is similar to that chart we showed you out of the KC-135 flight manual. The KC-1, go back one. KC-135 is a Boeing 707 platform, and here I've drawn some lines showing a 20,000 feet, and then 40,000 feet, 100,000 pound airplane, and a 130,000 feet airplane. So next slide, we're cruising somewhere, and let's say we're at 40,000 feet, 100,000 pounds gross weight at point A. Now there's to get to the low speed buffet boundary. Next slide. We slow down and we go to point B, where as you slow down, at some point you will get the edge of the burble and you will be in buffet.
Hey, Steve, let me just point out here for everybody to make sure everybody understands. You at point A, you're 1G at this particular point. Notice we got angle of attack on the left again and Mach at the bottom. So AOA is vertical. But here we are, point A, 1G flight. Now, as you decelerate, you're, of course, trying to maintain 1G level flight, your AOA is going to go up, of course. And that's what we're showing here. As you work your way up the curve to the left, you eventually get to point B.
Right. If you slow down, obviously your Mach decreases, and if you maintain level flight, you will your angle of attack will increase. Now let's go to high speed buffet. If you speed up 1G, level flight or in a dive, which is about 1G, you'll get to point C. This is theoretical, this point C. At this point, we don't know where point C is, and that's what we're going to talk about. The other way to get to the buffet boundary is to turn. So if I turn at 1.3 Gs, I multiply my gross weight by 1.3. So I'm on the 130,000 pound line on the chart. And at that, if I maintain my Mach in the turn, I go to point D and I've got buffet onset. So those are the three ways the three maneuvers you do to get to the buffet boundary. Now let's answer that question about what point D is. Next slide. Like I said, well, it's point C on this chart. So point C is somewhere, maybe. And as I said, it's going to be beyond MMO. Next slide. That point C, if it exists, is greater than MMO. So that's the point I wanted to make for you guys this morning on the high-speed buffet. I think it's emphasized too much in some companies and some training material because you just won't get the Mach buffet in level flight.
So, okay, point A, we're presuming that we're below MMO of some
Right.
margin, and if you work your way toward point C, you've exceeded MMO, and you are probably somewhere. You've even potentially even exceeded MD, depending on the design of the airplane. Now, I understand you can have some buffet past MMO all the way out to MD. You can have some buffet. You just can't have controllability problems, that kind of thing. Is that correct?
Yes.
Okay.
Yeah. But at or below MMO, you cannot have that high-speed Mach buffet.
Okay. Awesome. Good stuff. Good stuff. I mean, we've touched on one of the main aspects of the value of high altitude UPRT helping pilots to deal with compressibility there, and that is the value of getting transonic UPRT because we do need as jet pilots to understand compressibility and its effect. Also, what the OEMs do to certify the airplane, where our maneuver and controllability margins are, and then how to appropriately react to excursions, such as an overspeed excursion, all right, or even a stall type excursion as well, such as a high altitude stall. We've got engine performance not problems, but degradation up there as well. There's a lot of topics that should be considered and trained in for high altitude jet pilots. Fair to say, Steve?
Yes. The gap right now is that we have very few opportunities to manually fly in the transonic region. So any UPRT provider that has a platform that will go up high and you can experience the change in handling qualities and do some high altitude stalls, do some energy management. Energy management as the way you learned it from the old FAA approach to a stall, to stick shaker, and then energy management at low altitude is with your right hand pushing the throttles up. Energy management at altitude is with both hands or the stick, and you have to use the vertical. To use a fighter pilot terminology, to manage your energy, you have to work the vertical at high altitude. And you can do some of this in the simulator. And I hope they're doing high altitude stalls in the simulators with the extended envelope data packages. I don't know if the simulators, it's my opinion, the simulators do not replicate the buffet. It doesn't feel the same in the simulator it does in an airplane, because that box that's sitting on those 6 hydraulic pistons, it just can't be shaken the same way that the air will shake an airplane. So you probably don't get a good feel for buffet onset in a simulator.
Accurate feel, and I totally agree with you. We got to be careful about simulator high altitude training. We got to make sure the model is valid there, and we're getting representative characteristics of performance up there. It's one good thing about getting in an actual jet and going get some high altitude UPRT we've been doing that for a number of years now, and it's just so well received. Pilots are just fascinated to be able to hand fly the airplane up at altitude and see the difference between it and low altitude.
Right.
So we've really agreed here, transonic UPRT, good thing to get. But now, what about supersonic? What about supersonic flight, Steve? Can you imagine at all why would a say business transport category jet pilot flying a Gulfstream or Citation or even 737? What is there that he needs to know about supersonic? And is there value in getting supersonic experience?
Well, I'll tell you what, Otter, if you guys buy a T-38, I will be more than happy to be your supersonic demo pilot.
Okay.
And there certainly, if you did that, there would be some things you could learn about supersonic flight, the transition from subsonic to supersonic. Includes some changes in the stick forces that are required to fly the airplane, and you would see those. But if I were a flight department manager, director, and looking at that type of training as opposed to other types of training, I don't think I can make a business case for it. I don't know that there's any learning objectives that would apply to a transonic transport airplane. I would rather, for the guys in my flight department, to fly in the high altitude, do some hand flying high altitude, or do more unusual attitude recoveries than do supersonic. So we got some designs out there for supersonic business jets that are just around the corner. So not too far in the future, we might have a need for supersonic training. I don't think you can do an upset. You can certainly show some of those differences in stick forces and stability that happens, but you're going so fast, you really can't lose control. Unless you go into a high-speed dive, and then you can break the airplane up. I don't know at this point in time what the value of that would be.
I would agree with you, Steve. We've both flown supersonic aircraft before, but they were very specialized and designed to go there. But our transport category jets are not designed to go there, and it introduces a whole lot of problems once you exceed MD or as you enter that supersonic realm. You have a risk of the airplane just breaking up there. So again, we just don't see a value. Certainly if you want to go fast, get in the T-38 and go fast and get a T-shirt therefore it's certainly not going to dissuade that. However, from a training standpoint, little to no value. In fact, I might even say there's a risk of negative training. It's possible that a pilot could think that he's got some survivability in the supersonic speed range in his transport category airplane, and that's just not the case.
One thing we didn't talk about is the drag rise that happens as you approach sonic speed in one of these types of airplanes. You probably can't get supersonic because of that drag rise as you descend. I couldn't even get the A7 to go supersonic. It has this great big intake in the front, and some of the pilots say that they could go vertical dive and get it to 1.05, but the drag rise prevents us from going supersonic. So you need one of these. You guys buy one of these, and we can go supersonic.
There you go. All right. So I think we've pretty well agreed. Absolutely getting high altitude transonic UPRT in an appropriately validated simulator or in a high altitude jet there is good training, but supersonic, little to no value there. That kind of brings us to the end. I know we went just a little bit long here, but let's jump into the Q&A here. Random, what are you showing for some questions for us from the audience?
We have three things that we would like to look at. The first question that we're going to consider is, what is mock tuck? Is that something that I should be worried about in my airplane?
When you look at aerodynamics material textbooks or papers and learn about transonic effects, they usually present it from the perspective of a subsonic optimized airplane and what bad things can happen to it as you go into the transonic regime. So the term mock tuck was coined back in the World War II era and the post-World War II era from those straight-wing fighters that would go into a high-speed dive and get into compressibility effects, and it would sometimes blank out the tail, so they would be in a dive and their elevator was no longer effective. At some point, the nose would drop and they could come out. Today, in our airplanes, in all airplanes that go transonic, you will get a shift in the point where the center of lift will move back. And, the lift is trying to move the nose down, and the tail balances that to keep it level. So if the lift moves back, it may actually get smaller, but it moves back. So the moment of the lift tends to go nose down. And that will happen in most airplane design, most of the airplanes we fly. So it's not really a tuck. It may be a fairly small band of Mach where that occurs, like 0.78 to 0.8. And there will probably be an automatic trim feature called Mach trim that moves the stabilizer. When Mach tuck was first noticed, those airplanes had a fixed horizontal stabilizer with an elevator. Now we have an all movable stabilizer where we can adjust that and keep the airplane balanced. The Challenger 300 and 330, 350 has a switch called Mach trim, and so most airplanes today will have that. It's a trim change, but it won't be a violent nothing. You don't notice it because you're on autopilot.
Steve, you can't. The airplane cannot display a Mach tuck tendency in any way, even from MMO all the way out to MD. Is that correct?
You might get it beyond a change. Now the upset recovery training aid version 2 and 1 and the high altitude supplement, they don't explain that correctly, in my opinion. they say that mock tuck happens after MMO, and I say that the increase in mock nose down trim change happens before MMO, and that's why we have on the Challenger and 767 has a mock trim, and it's on a schedule that the engineers figure out where they should adjust the stabilizer without. You don't have to move the trim at all. You just.
That's the beauty of having you, Steve, to provide that level of nuance. One of the things as I was listening to your conversation is that this is the kind of information that unfortunately we don't always have the time to provide in the 142 Training Center getting a type rating. But I think a lot of the folks listening really benefit from it. We've got a question from another U.S. Air Force Test Pilot School grad, a friend of ours, Paco Uberta, is probably calling in from New Zealand. That's where he was last seen or heard from. And Paco says, hi, Steve, regarding the statement that Part 25 airplanes cannot have wings level 1G high-speed buffet up to VMO, MMO, does that mean it just cannot be perceived by the flight crew, or that the airplane has to be completely free of vibrations / disturbed airflow that might be sensed somewhere on the airplane other than the flight deck?
Well, hello, Paco. Paco and I have known each other for a long time. We were test pilots at Bombardier on the C series, which is now the A340, and so we've both moved on from that. And I think to answer your question, one of the issues when we do buffet boundary testing, and we are required as the OEM to define the buffet boundary and to publish that data in the AFM, the Airplane Flight Manual. When we do that, the onset is subjective opinion of the pilot. And of course, the engineers do not like that. They like to deal in numbers. So they will use some accelerometer data, and it's a G meter, a G sensor that's mounted underneath the pilot's seat. So it gives the pilot's station variation in G. And they typically say if you get a peak-to-peak oscillation in G of 0.05 to 0.1 G, that is onset of buffet. So if you got that amount of G at the pilot station, it would be considered buffet, and it wouldn't pass the regulation. If you got some, you might have some vibration. There's, the engines cause some noise and vibration, but when we're looking at this type of G buffet or Mach buffet, it's not allowed up to MMO.
Okay, so Paul B.J. Ransbury, the CEO of APS, is watching from home today, and he's going to make you put on your thinking cap here. Steve, he says, in your judgment, what proportion of upset awareness and prevention is the responsibility of licensing and certification compared to the portion being the responsibility of a UPRT program, given the limited amount of time pilots and the flight departments invest in UPRT solutions? So I think he's asking, is this the regulator's job to make sure that pilots have the type of training that they need in this environment, or should that be the responsibility of a UPRT provider?
Well, we're seeing regulations like you mentioned, the stall training regulations. You were on 109, so the regulatory agencies have stepped in and required at least advanced stall training and simulators that have aerodynamic data package that you can train without getting negative training. So the problem, of course, with the simulators is that it's not real. You don't get that startle factor. We watched a video from you guys from the extra where the pilot, airline pilot, went upside down and he almost couldn't function. So the regulators say you have to do the training, but we want to do some part of this training in an airplane. And that's where the UPRT providers come in. And you guys are the only ones that can do that.
Yeah, those human factors are impossible to entirely replicate in the simulated environment. We've got just a couple of minutes here, guys, before we have to go. Another question that we had is, why isn't critical Mach indicated on the PFD, Steve?
Well, it's not critical, for one thing. Critical Mach is a term that applies in the classroom to the study of a two-dimensional airfoil. And at some speed, some Mach, there will be a shock wave that will form, and that is called critical Mach. On an airplane, you can see we have no, on a swept wing jet, you have how many different airfoils are in that wing. If you look at the wing ribs inside there, every one of them is a different shape. So you got how many different critical Mach numbers. And oh, by the way, you don't have a airspeed indicator or probe, pitot probe on most airplanes on the wings. It's up here where your airspeed comes from. So with the advances we have now are swept wings, better design wings for control of delaying that trim change, a flatter on the top of the wing, then a high cambered, sometimes called a supercritical wing design. We've pretty much designed out, so it's not critical that you know when your critical Mach is exceeded. You're more concerned about flying at a optimum Mach number for time versus fuel used, econ cruise speed, and you don't have to worry about critical Mach.
So it sounds to me like the most critical thing about critical Mach is just the name, not the reality.
Yeah, in aerodynamics, they use the term critical a lot to mean a change, sudden change, a peak point in some parameter. It's critical Mach. You see critical angle of attack, which is again in the classroom for a two-dimensional airfoil, and it's not critical like there's danger.
Well, I want to thank you very much. We're about out of time, Steve, but is there any parting thoughts you'd like to make to the audience before we sign off today?
There's a lot more detail available. You guys have some courses. You might want to put a link in there that goes into high altitude stalls. I gave that presentation, and high speed, how we derive VD, MD, how the flight test, what that all means to you. So there's, I hope this got you thinking, and if you want more, you guys can tell them where that information is available.
And we're going to do that, Steve. Steve was gracious enough a year ago to do an entire webinar on high-speed flight testing that he's done in both the civilian and military worlds. And if you go to the APS website, you'll be able to see that. That's available as a video course. But I'm afraid that's all the time we have for today. So we'll say goodbye to everybody. We've had folks from over a half dozen different countries joining us, and just really glad that you could join us to share all of your expertise, Steve. So
thanks,
Steve.
Steve, it was great having you again. Thanks, Randy, for getting us going, hosting this.
You bet. Bye-bye.